Hi, everybody. Thanks for coming to my talk. My name is Zhixuan. I'm a software engineer at Tinder. Before I get started, how about we have some fun? Right, everybody? Raise your hand if you love superhero movies. Yeah? Great. Most of you are like me. And raise your hand if you don't know who she is. She's Scarlet Johansson, the Black Widow from the Avengers. Unfortunately, we're not going to watch a superhero movie today. However, I'm going to show you something just as awesome. We'll be talking about Scarlet, a library we created at Tinder that makes WebSocket on Android as simple as 10 lines of code. Has anyone used WebSocket before? Cool. WebSocket is a communication protocol for real-time applications. It creates a persistent connection between client and server. Just like a phone call, it's bidirectional. The client can send messages to the server. The server can also string messages down to the client. Let's see it in action. Here's how you will create a WebSocket connection in JavaScript. You can listen to when the connection is open and send a message to the server. You can also listen to messages from the server and process them. That's pretty cool, right? However, if you're new to WebSocket or its alternative, you'll probably be wondering, when is WebSocket useful and what problems does it solve? Ultimately, how can WebSocket help you build a better app? Well, it really depends on your business requirements and how real-time your features need to be. Most apps work fine without a real-time connection with the server. However, if you're building chat, location sharing, or online games, you'll probably appreciate having a real-time connection like WebSocket. At Tinder, we started using WebSocket last year. It helped us deliver matches and messages faster and more efficiently to all of our users on Android, iOS, and web. Before I show you how WebSocket made Tinder a better app, let me introduce to you how Tinder works. Tinder is the most popular app in the world for meeting new people. We spark millions of connections every day. When you open Tinder on your phone, the first thing you will see is a stack of people nearby that we think you will be interested to meet. You can tell us whether you are interested by swiping left or right. A left swipe means you want to pass, and a right swipe is a like. Let's swipe right on Scarlet to like her. And if Scarlet also likes you, then it's a match. You can start a conversation immediately if Scarlet has already swiped right on you. However, if you are the person who swiped right first, your profile will show up on her app very soon, and you'll receive a match when it happens. Since we already have a match, let's start chatting. Eventually, if you enjoy chatting with each other, you might go on a date together. As we have seen, swipe, match, and chat constitute the core Tinder experience. In order to deliver the best Tinder experience, our app needs to get new matches and new messages from our server in real time. How does the Tinder app do that? In the beginning, we started simple. The app makes a request to the server every 2 seconds to ask for updates. If there's no changes on the server will return an empty response. The app will check back later, every 2 seconds. However, if there is a new match, it will be sent to the client the next time it asks. This form of communication is called polling. Polling is easy to implement in code. It's probably not the best practice, but it worked for a long time. During this time, Tinder grew its user base exponentially. We now have users in almost 200 countries, and we deliver 26 million matches every day. At Tinder scale, the cost of polling is prominent. Our server is flooded with requests from millions of devices because each device makes a request every 2 seconds. After running some numbers, we found out that 90% of the requests get an empty response. What does that mean? It means that all these empty responses are unnecessary overhead. Although they do not carry any useful payload, they have a long list of headers that cost server CPU and bandwidth. If we can avoid making those requests, we could downsize our server and save a lot of money. Besides the cost issue, polling also has a longer latency. If you make a request every 2 seconds, no matter how fast your internet is, you could experience a 2-second delay. Because polling is expensive and it has a longer latency, we decided to switch to a push model. And our backend built a new infrastructure that can push new matches to the app. Using the push model, the client can subscribe to the server, and matches will be sent to the client through a persistent connection. There are a lot of technologies out there that can be used to push data to the client. For instance, there's WebSocket, Socket.io, and MQTT. We chose WebSocket, which is widely supported on all the platforms we develop for, Android, iOS, and web. Compared to long polling, WebSocket is much faster. Messages are delivered instantly in the most efficient way because we only consume the bandwidth needed by the payload. Okay, let me get some water. So last year around this time, I was given the task to integrate the new WebSocket API in our Android app. As I mentioned before, I'll use this WebSocket connection to receive new matches from the server so that our users can see them as soon as possible. I'll also use the WebSocket to send and receive chat messages. Let's take a closer look at the Tinder app. Here are 3 views that are driven by real-time data. When the app receives a new match, the It Match screen on the left is launched. The match list, which is in the middle, displays all your matches. We show the new matches on top and the matches you have already talked to on the bottom. When the app receives a new match, it will be added to the top of the match list. Finally, we have the chat view on the right, which involves sending and receiving messages from the server. Okay, let's explore how chat view interacts with our WebSocket API. In the high level, the chat view is consisted of 3 subviews. A recycler view that displays the conversation, and edit text where the user can compose messages, and the send button that sends the message to the other user. The view logic of this chat view is encapsulated by a view model. The chat view model has 3 properties. It has a live data that provides messages to be displayed on the recycler view. Since we don't want the user to send messages when there's no internet connection, we use a isConnected live data to disable the send button when the app is offline and enable it when the connection is back. In addition, when the user clicks on the send button, the view will call the send message method on the view model. This is all pretty straightforward, but to feed these live data, we need WebSocket libraries. We need a WebSocket library. There are a few options available, and we chose OKHTTP. OKHTTP added WebSocket support in 2017. Let's take a quick look at this WebSocket API. To create a WebSocket connection using OKHTTP, you will use this method. It takes two parameters. The first one is the request, which contains the server URL. The second one is a listener object. You can use the listener to listen to the connection state, and you can also use it to listen to incoming messages. To send a message, however, you will use the WebSocket object. Now that we have a view model, and OKHTTP, let's see how they interact with each other. Here's the data flow diagram that represents the chat view and what's happening behind. On the left, we have the UI, and on the right, we have network. Let's see what happens when the view is attached to the view hierarchy. The view model will try to open a WebSocket connection using OKHTTP. And after the connection is open, the view model gets a callback from the WebSocket listener, and it updates the isConnected live data to be true, which then enables the send button. And when we receive an incoming message from the other user, the view model will receive the message from the WebSocket listener, and then it will update the message live data so that the recycler view will have the new message. After the user has composed a message and hit the send button, the send message method on the view model is triggered, and the message is forwarded to OKHTTP. These are all the interactions between components. It's easy to understand, right? But it's not correct. It's a naive implementation because it did not take into account connection failures. As programmers, we tend to focus on the happy path and overlook the edge case. WebSocket is straightforward when the connection is open. However, things can get complicated when you need to recover from connection failures. A WebSocket connection can fail for many reasons. It can fail when you are on a train passing through a tunnel. It can fail when the server is out of memory and tries to release resources. Let's take a look at the happy path. On this diagram, the horizontal axis is time, and the vertical axis represents the connection state. When the user is not in the app, we don't want to open the connection. As user opens the app, we open the connection and keep it open as long as the user is in the app. This is simple and straightforward, right? What should we do when the connection fails? Let's take a look at this error scenario. So the connection is opened. However, the server crashes for the 4th second. what should we do? The client should, because the user is in the app, the client should retry the connection again and again until the server is back on. Right? In order to implement this retry logic, we need a timer. The timer has a simple API. You can schedule a retry and get a callback using the timer listener. Given the connection is opened successfully and the send button is enabled by the view model, the connection may fail at any time, and the view model will then have to disable the send button, right? And as it does that, it also schedules a retry with the timer. And a couple seconds later, the timer ticks, and the view model gets a callback and opens the connection again. With the retry logic, we can we can keep the connection open, and all the things we need to do to keep to implement retry is here. Unfortunately, this is good for the web, but it's not good enough for Android apps. On Android, we don't want to keep the connection open at all times. According to the developer guideline, we should only use the connection, and we should close the connection when the app is in background, in order to be a good citizen and save users' battery. In order to react to activity changes, lifecycle changes, we can subscribe to a lifecycle owner, such as an activity, a fragment, or the app. We use a lifecycle listener to listen to when the app is in foreground. When the app is in foreground, the view model will get a callback and opens the connection using OKHTTP. When the lifecycle owner when the app is in background, however, the view model will also get a callback and closes the connection using the WebSocket object. Suppose the app is in foreground again, and the connection fails. Right. No worries. The view model will schedule a retry, and it will bring the connection back on. Suppose the connection fails again. The view model schedules another retry. But this time, the app goes to the background. What the view model needs to do is cancel the timer. Look at all these asynchronous events that you need to handle just to add WebSocket to your app. I know what you guys are thinking. You must be lost, right? This is exactly how I felt on my first day at Tinder 2 years ago. We had this giant singleton manager objects made out of thousands of lines of spaghetti code. Let's take a look at the chat view model again. The view model is overloaded with different responsibilities. Guess how many lines of code this view model has? I think it will take at least 1,000 lines of code to write in Java. And thousands of lines of spaghetti code to add WebSocket to your app in 2018, that's exactly the motivation behind Scarlet. We created Scarlet to make WebSocket simple on Android. Instead of having a giant view model that takes more than 1,000 lines of code, you can leave the complexity to Scarlet and write the view model in just 10 lines of code. Okay. So what is Scarlet exactly? Scarlet is the first WebSocket library that minimizes boilerplate code and spaghetti code that you need to write. Scarlet is declarative. You only need to describe what your endpoint looks like, and Scarlet will implement it for you. Let's continue the chat example using Scarlet. Here's the code you need to write to declare your endpoint. You need to declare an interface and use Scarlet to create an implementation of the interface, just like in Retrofit. Let's go through the methods one by one. To send the message to the server, you need to declare a method that has the send annotation and specify the object you want to send, which is a message in this case. After you create an implementation of this interface using Scarlet, you can use this method to send the message to the server. To observe connection state, however, you would need to declare a method with the receive annotation, and the return type will be a flowable of WebSocket event. After you created an implementation of this interface, you can subscribe to the connection state and log them. To be able to receive incoming message, it is similar. You only need to change the return type to the message type you expect from the server. And after the server is created, you can subscribe to it. Just to recap, we created an interface with three methods and used Scarlet to create an implementation. Let's use it in the chat view model. Right? And we have a messages live data. We can simply convert the incoming message string we can aggregate the string to become a list and the view will then be able to consume the messages. And for the is connected live data, you can simply transform the live WebSocket event and pass it to the client. Finally, we have a send message method, which delegates to the chat servers. Just to recap, we declare three methods on the interface, and we use Scarlet to generate an implementation. Then we created a view model in just 10 lines of code. Besides being declarative, Scarlet is also modular, meaning that it consists of modular components that can be changed independently. To see how modular Scarlet is, let's dive into its implementation. As a WebSocket library, the Scarlet needs to implement the WebSocket protocol, and it uses OKHTTP under the hook. Instead of using OKHTTP directly, we created a well-defined interface around it. And this interface hides the specific WebSocket implementation from Scarlet. It so that Scarlet can work with any WebSocket libraries that you prefer. Just to clarify, Scarlet does not have code dependency on OKHTTP. Instead, it uses it as a plugin. In order to keep the connection open for you when the connection fails, Scarlet schedules, it uses a retry timer internally, and you can customize the backoff duration using the backoff strategy plugin. Again, when the connection fails, Scarlet uses the backoff strategy to determine when to retry. Next, in order to close the connection and stop retrying when the app is in background, Scarlet listens to the lifecycle owner, and this is also done using a dependency inversion, so that Scarlet can be a pure Kotlin library, and it does not have to depend on Android. A lifecycle has two states. A lifecycle in Scarlet has two states. It has the name as the one in Android architectural components, but they are different. A lifecycle tells Scarlet when to connect and keep retrying. When the lifecycle is on and the connection failed, Scarlet will keep retrying. These plugins allow Scarlet to take over state management from you so that you don't need to write any spaghetti code. The real benefit of having plugins is that no matter what library you prefer to use, you can use it with Scarlet. For instance, in tests, you can use the mock HTTP server, which lets you mock the server behavior. And of course, you can also write your own plugin. Plugins are easy to write because they are designed to be customizable. If you write your own plugin someday, please create a PR and share it with us. Similarly, backoff strategy is also a plugin. We have a few built-in implementation, and you can write your own as well. For lifecycle, we have built-in support for Android. You can write your own lifecycle, and you can also reuse them by composition. I'll get to this later. Okay. So let's see how you will create a Scarlet instance in code. If you're starting from scratch, like we just did, here's the recommended configuration. First, create a Scarlet builder and add a WebSocket plugin that is based on OKHTTP. Then you can choose the backup strategy you prefer. I believe we have a default one. And then you can use to scope the WebSocket connection. You can use our built-in Android lifecycle plugin, which only opens the connection when the app is in foreground. And here we go. Here's how you create the WebSocket instance for the chat view. However, something is missing here. So how did Scarlet know about how to serialize and deserialize messages? And do you have to use Flowable? It turned out that Scarlet has two more plugins for customizing these behaviors. Let's go back to the list of plugins. Okay. Scarlet supports using Moshi, JSON, and Protobuf to do data serialization. This is done through an interface called message adapter. The message adapter has two methods. It takes your data. One takes your data and turn it into the data structure the class that you want, and the other serializes a class to a string or bytes. As we saw in the previous example, Scarlet supports Flowable from RxJava. It also supports coroutines, and this is done through string adapters, which enables Scarlet to support any asynchronous abstractions that you prefer. And Scarlet is able to support these behaviors without any code dependencies on those libraries because it uses them as plugins. Okay. So how do you customize message adapters and stream adapters? All you need to do is to add them to the Scarlet builder. Once set up, you'll be amazed how easy it is to maintain Scarlet. Let's say you want to make chat more engaging by adding a typing indicator feature. How many lines of code? Guess how many lines of code we need to change to be able to send typing indicators to the server. We only need to change 2 lines of code, like this. Similarly, switching JSON library is also a 1-line change. All you need to do is pass a different plugin to the builder. And at Tinder, our WebSocket connection is only enabled when the user is logged in. If you want to further scope down your WebSocket connection to when the app is in foreground and the user is logged in, you can do it in less than 10 lines of code. First, you need to first grab the built-in lifecycle plugin that describes when the app is in foreground, and write your own lifecycle plugin that represents when the user is logged in. Then you can simply combine these lifecycles, and Scarlet will only connect to the server when the app is in foreground and when the user is logged in. Let's wrap it in a function and pass it to the builder. Cool. Scarlet, we have seen how Scarlet is declarative and modular. Because of that, using Scarlet makes your code base clean. But is Scarlet well-written and maintainable? In other words, is Scarlet written in predictable code? The answer is yes. Although state management is complicated on Android, Scarlet is not written in spaghetti code. It's actually very testable and debuggable because it uses immutable states, and it has a state machine internally. We actually wrote a Kotlin DSL for writing declarative state machines, which is available as a separate library. Let's take a detour to see what a DSL looks like. This is a water state machine. We all know that water has three states. It can be solid, liquid, and gas. And there are 4 possible transitions between them. Let's model the state machine in Kotlin. First, we need to declare all the states. And then we need to declare all the events, which triggers the state transitions. Next, we can use the state machine DSL to declare the state machine. A state machine has an initial state, which is solid. When the state is solid and it receives an unmelted event, it will transition to the liquid state. When it's in the liquid state and it receives an unfroze event, it will transition to the solid state. And similarly, we have, you can declare other transitions like this, and it's simple and readable. After, it's simple and readable, but it's also testable. After the state machine is created, you can assert the initial state to be solid. And you can also test the state transitions given an unmelted event. We just saw how declarative the state machine is. Here's the state machine that Scarlet uses internally. It's simple and elegant, and it's customizable. This is how they use the lifecycle changes to keep the connection open. And when the connection fails, it uses the backoff timer to recover the connection. This is the state management in Scarlet. Let's move on. And just to recap, Scarlet is declarative. It makes WebSocket as simple as 10 lines of code. It's also modular. You can use any WebSocket or JSON library with Scarlet. Scarlet is also predictable because it's driven by an immutable state machine. Since Scarlet was released in June, we received a lot of feedbacks from the community. The most wanted feature is supporting more protocols. We are working on a V2 to address this need. Supporting different protocols is challenging because they are very different. For instance, not every protocol is bidirectional. Server-sent event only allows server to string messages down to the client, but not the other way. While WebSocket and server-sent event only have one channel, other protocols support the concept of topics, and which behaves like message queues. And for instance, if you're building a chat room app, you can have a new message topic for incoming messages, and maybe a user count topic that notifies you when a user joins or leaves the room. Finally, we Stump and MQTT do not talk to the server directly. They talk to message brokers, which then forward the message to the server, to your backend. In order to support all these libraries, we made a lot of changes in Scarlet. We rewrote half of the code that is in Scarlet. And let's take a look at all the plugins Scarlet has. Here's what we did. In Scarlet v2, we climbed up the ladder of abstractions. We took the WebSocket plugin, the WebSocket abstraction, and turned it into a protocol client. So by doing so, we're able to support any persistent connection protocols available. Okay, unfortunately, we don't have time to go deeper into the details, but I would love to discuss with you later after the talk. The source code is available on this branch, and it's been published to Jetpack. As you can see, we have different artifacts in V2. And please check out the demo app. We have added server-side event and socket IO to the demo app. Here's this sneak peek into Scarlet v2. And I cannot wait to discuss it with you offline. And that's pretty much all I have for this presentation. Just to recap, Scarlet is declarative. I mean, it's easy to get started for beginners. It's also customizable for advanced users. Because it's predictable, because it's driven by a state machine, it's also predictable. And finally, Scarlet is evolving. We're adding other protocols to, in addition to WebSocket. I hope Scarlet can make your life easier. And here's how you can get started today. And I'll be around today and tomorrow. And feel free to grab me and check out, and please check out our booth. We have a Tinder booth in the lobby. Yeah, and that's it. I'm happy to take any questions.